Hello and welcome to Lecture 1 of Traveling Waves in Phys 1201. And in this lecture we're going to start a two-topic unit look at waves. Waves are probably one of the most important ideas in all of physics. The first thing to realize about waves is that waves are not objects in the sense of the sorts of things we've been looking at in Physics 1101 and at the first little bit of this course. They are disturbances that travel through objects. So we have something. I don't know what it is. It could be the surface of some water, or it could be a rope or something like that. But either way, we call it the medium. It is the thing that the wave travels through. And the medium is disturbed in some way. So if this is water, perhaps a stone was just dropped in. If it's a string, perhaps somebody just grabbed it and gave it a little wiggle with their fingers. And then the disturbance travels through the medium, or we often say it propagates. A key thing to realize is that the medium itself doesn't travel. If you watch this wave traveling down this long spring, you'll see that there's a string tied to the spring at one point. And the piece of spring with the string attached to it does not travel. It just wiggles up and down as the wave passes it. But the other thing to notice is that if I start the wave by wiggling the spring upward, then I get an upward wiggle that propagates along through the spring. But if I start with a downward wiggle, then there is a downward wiggle that propagates through the spring. In other words, the shape of the original disturbance determines the shape of the wave, and the shape of the disturbance is preserved in the wave. It just propagates through the medium. One thing that takes some getting used to with waves is that there are two quite separate velocities or speeds that you need to keep track of. There's what we call the wave speed, which is how fast the wave itself travels through the medium. On the other hand, the speed or velocity, if you're worried about direction, that a piece of the medium is going at any time is called the particle velocity. So just to make that clearer, let's look at an example. Sports fans doing the wave. So here we have a snapshot of a bunch of fans, and this is a person at the crest of the wave. Their hands are as high as they're going to go. This person is about to start sitting back down. Over here is a person just ahead of the wave. They're just about to start standing up. The wave is going this way, so I say the wave velocity is in this direction. And a moment later, the wave looks like this. This person is now standing, this person has sat back down. And during that little time period, while the wave velocity was to the right, the particle velocity over here, what we mean by that is the velocity of people's hands, has been up. But the particle velocity over here has been down. This person has been sitting back down. And so notice how different those are. And in particular, the wave velocity has been to the right. It's a constant property of the medium. It's been to the right the whole time. But the particle velocity is different over here on the right than it is on the left. And it also differs from time to time at any location. It's been up here, but if we look again in another moment, it will have been down. You can get a sense for how different these two velocities can be by watching some actual sports fans doing the wave. So here they are, and if you watch the crest of the wave, you'll see that in about a second it passes through two sections of the fans. And counting across a section, I see there are about 10 people across a row in a section. And so our wave speed, so I'll say v of the wave, is, well, if the people are about a meter apart, which is reasonable, then that tells us our wave speed is about 20 meters per second. On the other hand, if you watch again, but this time don't watch the crest, watch a single fan as they stand up, you see that it takes them about a second to stand up. And so that tells us that the particle speed, the average particle speed during that second, so I'll say VP average. Well, they raise their hands perhaps 2 meters, and it takes them about a second to do it, and so this is about 2 meters per second. So there is a very large difference between how fast the wave moves along the stands and how fast the medium moves, a particle of the medium, in other words, a pair of hands, as the wave is reaching it. There's a seemingly endless variety to the types of waves that are possible. Every medium has different things that can be disturbed, and that gives rise to different possibilities for waves. A water surface, the height of the surface can be disturbed, and those are the familiar water surface waves that we see day to day. When you wiggle a string from side to side or up and down, you get transverse waves, the position of string particles, bits of the string. That's what's wiggling. Sports fans doing the wave, the vertical position of their hands is the disturbance, the thing that is wiggling. These are all examples where it's motion of things that is wiggling, and so we call these mechanical waves. But there are other waves that aren't mechanical waves. Now, sound can be thought of as a mechanical wave. Particles of air are moving, but it's more often thought of as a wave where the thing that is disturbed is the pressure of the air. Light, much harder to picture. The medium is the electromagnetic field, and what is wiggling is the values of the electric and magnetic field vectors. At this stage, you probably have no idea what that is. We'll meet these later in the course. A more easily pictured wave is this. This is a chemical wave. It's called the Belousov-Zhabotinsky reaction. It's a clock reaction, which means it can run forward from reagents to products, and then it turns around and runs backwards from products back to the original reactants, and it'll do this over and over again, which gives you the possibility of a wave, where nothing is physically moving here in this wave. The color changes you're seeing are because what is disturbed are the values of the concentrations of different chemicals. Ever since very early in Phys 1101, we've been working with the particle model, where we think of objects that are moving around as occupying points in space. And this is fine for us as long as we're thinking about objects translating from place to place. But now we're looking at waves, and they are something entirely different from particles, and you can't think about them in the same way. Now, before I go any further, I'll just preview something we'll see at the very end of this course by saying that when I talk about the particle model here, I mean the classical particle model. In any case, a particle is at a particular position at every time, whereas a wave is spread out through space. You can't give a position for a wave because it occupies a region of space. A particle has mass, but it makes no sense to talk about a wave as having mass. The medium it's traveling through may well have mass, but the wave itself doesn't. Particles obey Newton's laws, and you can use Newton's laws to solve for the trajectory of a particle, which is just the path that it follows through space. But waves don't obey Newton's laws. You don't push and pull on waves, exerting forces on them to change their paths. Their paths are determined by properties of the medium they're moving through. So, for example, when light passes from air into water, it bends. And it does that in part because its speed changes, its velocity changes, the direction of travel changes, and it does it instantaneously at the interface between the air and the water. You can't change the velocity of a particle instantaneously. That requires an infinite acceleration, which would imply an infinite force. But waves aren't moving and changing their velocities because of forces, and so it's okay for them to change their velocities in an instant. When two particles meet, they generally collide and either bounce off of each other or stick together. But waves pass through each other, and in fact, as we'll see in the next topic unit of the course, one of the things that really defines waves is the way they behave when they're overlapping with each other. Most waves can be classified as either transverse or longitudinal. In a transverse wave, if it's a mechanical wave where what's being disturbed is particle position, then the displacements of the particles are perpendicular to the direction of the wave propagation. For example, for this wave, traveling down the spring, the wave is traveling from left to right, but you can see the string tied around one piece of the spring, and as the wave passes by, that piece of the spring goes up and down, perpendicular to the direction that the wave is traveling. Water surface waves, waves on strings, are transverse, less obviously because it's not a mechanical wave and you can't see the actual vibrations, is light, which turns out to be transverse. Longitudinal waves, on the other hand, have particle displacements that are parallel to the direction of the wave propagation. For example, here's a slinky, and I have put a piece of tape around one coil of the slinky, and you can see that as a wave propagates by, going from left to right, that piece of the slinky moves left to right, parallel to the direction of the wave propagation. And compression waves on slinkies are about the easiest to picture of all of the longitudinal waves. Many waves through solids are longitudinal. Less obviously, sound as it goes through a gas or liquid is longitudinal. Not so obvious because you can't see it. We're going to focus on non-dispersive waves. And what that means is that these are waves where the only thing that determines the wave's speed is the material of the medium that the wave is going through. So, for example, if we look at waves on strings, it turns out that the speed of a wave on a string is determined by two things. It's determined by what's called the linear density of the string, the mass per unit length, right? So if that doesn't make much sense to you, think about guitar strings. The thin strings here on this side are light. Per unit length, they have low mass, and so they have a small value of linear density. These thick strings have a larger value of linear density. The other thing that determines the wave speed, though, is the tension in the string, and it turns out that the speed of a wave on the string is given by this, the square root of the tension over the linear density. So that tells you that if you increase the tension, if you tighten a string, you make the waves go faster on the string. If you replace the string with a thicker, heavier string, then that will reduce the wave speed. For light, it again depends on the material properties. In a vacuum, light goes at 3 times 10 to the 8 meters per second. But through glass, and it depends on what kind of glass, but it goes about 2 times 10 to the 8 meters per second. And sound is again determined by the material, but also by the temperature. At 20 degrees Celsius in air, it goes at about 343 meters per second, but in water, it goes 1,480. Now, what we won't look at is dispersive waves, where the wave speed is also determined by properties of the waves, such as the wavelength. And the simplest example of that is water waves, where, at least for long waves, longer wavelength waves travel faster than shorter wavelength waves. But that doesn't apply to any of these except for light going through glass, which turns out to be dispersive, but only slightly.